The solar system originated from a vast, cold cloud of interstellar gas and dust. This primordial cloud is known as the solar nebula. It was primarily composed of hydrogen and helium, the lightest elements. Trace amounts of heavier elements were also present within this nebula. The nebula was not static. It was slowly rotating in space. This rotation was a critical initial condition for the solar system's formation. Gravitational collapse is a fundamental process in the formation of cosmic structures. It begins with a disturbance, such as a nearby supernova, within a nebula. This disturbance initiates the gravitational collapse of gas and dust within the region. As the collapse progresses, the cloud contracts significantly. The contraction leads to a substantial increase in the cloud's density. The formation of a protosun begins with the collapse of a nebula. As the nebula collapses, its central region experiences increasing density and temperature. This dense, hot core then forms a protostar, also known as a protosun. The protosun, a nascent star, accumulates most of the mass from the surrounding collapsing cloud. Following the initial collapse, residual gas and dust remained in the cosmic void. This material began to flatten into a disk-like structure around the newly forming protosun. The flattening and rotation were driven by the principle of conservation of angular momentum. As the cloud contracted, its rotation speed increased, causing it to flatten into a disk. This rotating, flattened structure of gas and dust is known as the protoplanetary disk. Within a protoplanetary disk, the birthplace of planets, vast amounts of dust and gas exist. Microscopic dust grains are present, constantly moving and interacting within this environment. These tiny particles begin to collide with one another due to various forces. Electrostatic forces play a crucial role, causing the colliding dust grains to stick together. This process of dust grains colliding and adhering to form larger aggregates is known as coagulation. Coagulation is a fundamental step in the initial stages of planet formation, building larger celestial bodies. Early solar system aggregates grew through continuous collisions and mergers. These growing aggregates eventually reached kilometer-sized dimensions. These kilometer-sized objects are known as planetesimals. Planetesimals served as the fundamental building blocks for the formation of planets. In the early solar system, planetesimals formed in regions like where Saturn would later develop. These planetesimals exerted gravitational forces on each other, leading to mutual attraction. This process initiated a rapid growth phase, known as runaway accretion. Larger planetesimals grew faster by gravitationally sweeping up smaller, surrounding bodies. Planetary formation begins with the accumulation of planetesimals within a protoplanetary disk. These planetesimals are small, rocky, or icy bodies that orbit a star. Through gravitational attraction and collisions, planetesimals gradually coalesce. This process leads to the formation of a larger, more coherent body known as a planetary embryo. A planetary embryo possesses a solid core, marking a critical stage in planet development. Once massive enough, it begins attracting significant amounts of gas from the surrounding nebula. Planetary embryos grow within a protoplanetary disk, accumulating solid material. Upon reaching a critical mass, the embryo's gravity significantly increases. This enhanced gravity allows it to rapidly accrete vast quantities of hydrogen and helium gas. This crucial gas accretion phase is essential for the formation of a gas giant planet. A proto-Saturn, an early-stage gas giant, continuously accumulated mass within the cosmic void. This accretion process led to a significant increase in its overall size and density. As mass gathered, the gravitational forces within the protoplanet intensified. Consequently, the immense pressure at its core began to rise dramatically. This escalating pressure was accompanied by a substantial increase in internal temperature. These conditions were crucial for the subsequent development and maturation of the gas giant. Over millions of years, the proto-Saturn's interior underwent a process of differentiation. This process led to the formation of distinct layers within the planet. A dense, rocky, icy core developed at the center. This core was enveloped by a metallic hydrogen layer, then an outer layer of molecular hydrogen and helium. Saturn's interior generates immense heat through two primary mechanisms. Gravitational compression, a powerful force, contributes significantly to this internal heating. Radioactive decay within the planet's core also releases substantial thermal energy. This generated heat drives convection currents throughout Saturn's interior. These convection currents are responsible for the ongoing evolution of the planet's internal structure. As Saturn grew, its gravitational influence extended, creating a sphere of influence. Within this sphere, smaller clumps of material began to coalesce. These clumps secreted from the leftover disk material surrounding Saturn. This process led to the formation of Saturn's various moons. Saturn's iconic rings are a prominent feature in our solar system, captivating astronomers and enthusiasts alike. Two primary theories explain their formation, both involving celestial mechanics and cosmic debris. One theory suggests the rings formed from a small icy moon that ventured too close to Saturn's Roche limit. The moon's destruction due to tidal forces created the vast ring system, or they are leftover accretion debris. Saturn's rings are a complex and dynamic system, shaped over billions of years. Their evolution is primarily influenced by gravitational interactions with Saturn's numerous moons. These interactions sculpt the ring material, creating intricate structures and patterns. This ongoing process results in the diverse and ever-changing ring system observed today. Saturn, a majestic gas giant, now orbits the Sun as a fully formed planet. Its intricate ring system is a defining feature, adding to its cosmic grandeur. The planet's existence is a testament to complex processes of planetary formation. These processes unfolded over vast timescales within the solar nebula. Saturn's current state reflects the culmination of these ancient celestial events.